This section of the book is the formal, precise, totally complete definition of what a limit truly means and how to prove that a limit is what we say it is. This is a hard section. We're going to be spending a couple of days on it, and it's going to take a little time, but this video will sort of introduce the ideas, and we'll get to more and more formal versions of it in class in the next couple of days. So, here's the deal. How do we even know that a limit is what we say it is? For example, the limit of 4x minus 1 as x approaches 5. Now, we can all look at that and go, well, when x is close to 5, 4x minus 1 is close to 20 minus 1, which is 19. Great. But these terms like close to and approaches are kind of vague, right? So far, we don't really know that the limit is 19. We just sort of think it is. We've looked at tables to figure out limits, tables of values. We've looked at graphs to figure out limits. The problem with those guys is that they can never be completely accurate, right? There's always lots and lots of numbers in between any two numbers, no matter how close they are, and we don't know which one of those lots and lots of numbers is the actual limit. For example, if I was just looking at a table of values or a graph, I probably wouldn't have enough information to know that the limit is actually 19 instead of something really close to 19, like 18.9999782 or 19.000000004, right? I can't be sure. Those are close enough to 19 that my graph is probably not high enough resolution to tell. My table probably doesn't have quite the amount of data to be sure. So how can I be sure? Well, let's go back to thinking about what limits mean, what we've been saying, right? The limit is 19 means that the values of that function, 4x minus 1, approach 19 infinitely closely. That is, they get just exceptionally close to 19. They get closer and closer and closer and closer, right? That is, you can make 4x minus 1 be within any tiny distance you want away from 19, right? It gets so close that no matter how small of a gap you want there to be, you can get it gets that close. As long as you're taking x values really, really, really close to 5. Right? So I can make 4x minus 1 be super crazy close to 19 just by picking x values super crazy close to 5. So now we want to make precise those super crazy closes. So for example, right, we're thinking about trying to convince ourselves that this limit really is 19. And that would mean 4x minus 1 gets really, really close to 19. Well, how close does it get? Well, can we make it 0.1 or less away from 19? Right? 4x minus 1 is some distance away from 19. Can we make it 0.1 or less of a distance? In other words, can 4x minus 1 be between 18.9 and 19.1? Those are a distance of 0.1 away from the number 19 on the number line. Well, that's a nice inequality. I said in the sentence 0.1 or less, and in this inequality it's actually strictly less, not equal to a distance of 0.1. I really meant just less than, not 0.1 or less, but less than 0.1. So the inequality is correct. So I add 1 to everything there, and then I divide everything by 4, which is a positive number, so it doesn't change the inequalities. And I get that in order for 4x minus 1 to be in between 18.9 and 19.1, x itself, that number, just has to be between 4.975 and 5.025, right? That's the requirement. That's how close is close enough for x to be to 5. Right? If x is that close to 5, in between 4.975 and 5.025, which is a little interval around the number 5, if x is in there, then the same algebraic steps backwards will force 4x minus 1 to be in between 18.9 and 19.1. So the answer to can we make this distance 0.1 or less is yes, we sure can, as long as we pick x to be within 0.025 units away from 5, right? That last string of inequalities says x is less than 5 minus, or x is less than 5.025, which is 5 plus 0.025, and it's bigger than 4.975, which is 5 minus 5.025. Here's another way to do the same algebraic stuff. If you look at this absolute value, 4x minus 1 minus 19, and then the absolute values. That is exactly saying how far away is 4x minus 1 from 19, right? Because the distance between two numbers you can find by subtracting, but then what if you subtracted the smaller minus the bigger? It would be negative, and distances aren't supposed to be negative. So you do the subtraction and then you absolute value it, and that tells you how far apart those numbers are. So this is how far apart is 4x minus 1 from 19, and well, I want it to be less than 0.1 apart. I want that distance less than 0.1. I can now simplify what's inside the absolute values, right? 4x minus 1 minus 19 is 4x minus 20. And I can factor a 4 out. And because 4 is positive, I can bring it outside the absolute values entirely. 4 times the absolute value of x minus 5 needs to be less than the distance 0.1. And then I just divide by 4. And that inequality tells me the distance between x and 5 needs to be 0.025 or less, right? That's exactly the same information as we got the other way. I'm doing it this way even though it may seem less intuitive to most of you, because the absolute value sort of notation and language is the way that our formal definition actually will eventually work, right? So that last red line says the absolute value of x minus 5 is less than 0.025. What that means is x and 5 are less than 0.025 apart on the number line. The distance between them is less than 0.025. So it's the same information. As long as x is in there, that distance is so tiny it's less than 0.025, then the distance I cared about, the one between 4x minus 1 and 19, will necessarily be less than 0.1. Okay, but so 4x minus 1 is within 0.1 of 19. Can I make it even closer to 19? For example, still thinking about the same limit, can we make that function be within 0.002 of 19 instead of 0.1, right? That's much, much tinier distance. Well, exactly the same procedure. Think about where 4x minus 1 would need to be for that to be true, in between 19 plus 0.002 and 19 minus 0.002. Do some algebra, and we get that x has to be between 4.9995 and 5.0005. Which is perfectly fine. That is telling me how far away x can get from 5. Okay? So the next thing to look at is the other way to do the algebra, right? Think about the absolute values. The distance between function, 4x minus 1, and limit, 19. That's that subtraction and then absolute value. I want that to be less than 0.002. Simplify. Factor out the 4, and divide. And I get that the distance between x and 5 needs to be less than 0.0005. Okay, so same information. I arrived at it through a different sequence of algebraic steps that are actually equivalent. So can we make that distance very, very small, 0.002 or smaller? Yes, as long as we pick our x to be really, really close to 5. 0.0005 units away from the number 5. Okay, so the idea is no matter what tiny distance I wanted, 0.1, 0.002, 0.0000783, I could do this same series of algebraic steps and come up with a number that is how far away x is allowed to be from 5. Okay, so I'm still thinking about this limit, but what happens if I try to think, well, maybe the limit's 19.01, not 19 exactly. Could I do this same sort of stuff? Could I make 4x minus 1 be within 0.002 units of that number? Maybe that's really the limit. Can we do that? Well, notice that my limit has changed. I'm now thinking maybe the limit's 19.01. It's pretty close to 19. Might be right. Okay, well, this would mean 4x minus 1 would need to be within 0.002 units of 19.01. So you add and subtract 0.002 from that number, and you get this inequality. Add 1 to everything, divide by 4, and we get this. This is a problem, right? Because this doesn't say how close x is to 5. In fact, 5 isn't even an allowable thing. Things really, really close to 5 are outside of these requirements on x. So this isn't the kind of condition we want, right? For a limit as x approaches 5, we need to be thinking about how close does x need to be to 5. And here we're saying it needs to be, not more than 0.003 units from 5, but actually it needs to be at least 0.002 units away from 5. So it's not super close to 5. It's super close to 5.001, but that's not 5. Okay, so this isn't the right kind of condition. If we do it with the absolute value procedure, right, function minus this limit I'm thinking about, that distance less than 0.002, do some simplification, still can factor out a 4, although it's not as nice. Divide everything by 4. And this gives me the same information as on the left. X needs to be 0.0005 units or less away from, not the number 5, but the number 5.0025. Earlier when I was looking at the left, for some reason I thought 5.001 was in between 002 and 003, and it's not, so ignore that earlier. But 5.0025 is the number in the middle, and this says, okay, great, as long as x is that close to 5.0025, your function will be close to 19.01, but that has nothing to do with the limit as x approaches 5. That would have to do with the limit as x approaches 5.0025, right? So that's also not a condition that tells me how close x needs to be to 5. So this fact that the 5 is disappearing and is being replaced by some other number, 5.0025, tells me that this limit isn't 19.01 when x is approaching 5. Right? If x is approaching 5, we can't make that distance statement at the top true. Right? So the limit as x approaches 5 is not 19.01. Right? We could do it with 19, we can't do it with 19.01, so we are convincing ourselves that the limit truly is exactly 19, not some other number that happens to be close to 19. Okay, so let me sort of recap. This statement, the limit as x approaches 5 of 4x minus 1 equals 19, means the following. We can get the function 4x minus 1 to be within any tiny distance we want from the limit of 19, that y value, by controlling how far away x is allowed to be from the number 5, by saying how close does x need to be to 5 to get 4x minus 1 to be this distance from 19. So we have control over how close x is to 5, and we need that to guarantee that 4x minus 1 is close enough to 19. Okay, now I'm going to sort of replace some things with some variables. Okay, so we could have looked at a different function than 4x minus 1. We could have looked at 2x plus 3, or x squared, or sine of x, right? So let's just call it f of x, and I'll replace 4x minus 1 with f of x over here. 19 is the limit. Let's just call it L, whatever the limit is, right? L. And we don't always want x to approach 5. We want x to be able to approach lots of different numbers, lots of different limit situations, so I'll just call the number that x is approaching a. Okay, so now we have limit as x approaches a of f of x equals L means we can get f of x within any tiny distance we want from L by controlling how far x is allowed to be from a. Now, there's notation here. A tiny distance, the distance between the function and the limit, is traditionally written with this. It looks like a backwards 3 or a kind of curvy E. It's a Greek letter epsilon. There's actually several different kinds of fonts you can write epsilon in, but this is the one I'll use. And how far x is allowed to be from a, we will be calling another Greek letter delta, but we'll use this lowercase delta, not the triangle kind of delta, because it's even tinier change than usual. Right? So epsilon and delta are tiny, tiny distances. Okay. So another way to restate what's right above is that we can make the distance between f of x and L, right, any tiny distance we want, we can make that distance smaller than any tiny number we pick by choosing how tiny to make the distance between x and a, the absolute value of x minus a. That is essentially the definition of limit. Now, there's a slightly more formal way to say it that we will see in class, but that's the idea. That's what a limit statement means. As x approaches a, the limit of f of x equals L means the thing in that orange box. All right. Hope that made some sense. I will see you in class, and we'll keep thinking about these ideas.